Hi there, this episode dives into object-oriented programming in Zig language. If you are interested in low-level development, or you are curious how VTables works, that episode is for you. Not into programming, but you ended up here anyway, you are more than welcome to stick around. So what makes object-oriented programming in Zig unique? The fact that Zig isn't object-oriented programming language at all, but that doesn't mean object-oriented principles can be applied. Even in our old friend C, developers have long used OOP-inspired patterns to simplify complex implementations. In my hobby project, where I'm building an operating system for the RP2350 microcontroller, I've reached a stage where I need a robust approach to integrating new drivers and file systems. Looking at the real world, Linux contains a virtual file system for that purpose. So using a file system interface, we can represent not only file systems like ext4 or FAT32, but also drivers for character devices, processes, and hardware information, like for example the proc.mem.info pseudofile. Almost everything can be represented as a file, making the operating system versatile. Thanks to that approach, I need only basic operations like read and write on files to get hardware informations and to drive hardware. Exactly the simplicity I was after. But my OS is implemented in Zig, so I started by handcrafting interfaces, VTables and FAT pointers, very similar to how allocators are implemented in the Zig standard library. And it worked, but the amount of boilerplate required for each new implementation quickly became overwhelming. So I built the module for object-oriented programming in Zig language, and closely mirrors C++ polymorphism. The key differences arise from my choice to keep it lean. Just as simple features that I actually need. Let's check out the demo using some basic polymorphism examples with animals. We will define an iAnimal interface. Each animal can speak, describe itself, and play with some toys. Animal-based class inherits from this interface, providing a generic implementation of the describe method, and also it is storing name and age information. The target implementations cat and dog both implement the speak and play functions. However, dog includes an additional bread field and overrides the generic describe method. In C++, the implementation of the design might look like this. Let's define an iAnimal class in C++ with pure virtual functions speak, describe, and play. Naturally, since we are using polymorphism, it also includes a virtual destructor. Animal-based class inherits from iAnimal and holds two member variables, a std string for the animal's name and an integer for its age. A constructor initializes these fields, and a describe member function provides a simple way to print the animal's name and age. Both cat and dog classes derive from animal base. The dog class adds an extra member field bread, represented as a standard string. Its default constructor accepts the necessary parameters to initialize both its own and inherited member fields. The speak method uses the name field from the base class to output a sound to the standard output. The describe method is extended to include bread information as well. And my dog doesn't like to play with anything. Most probably I have to call it Grinch. Similarly, the cat class has a default constructor that simply forwards initialization data to the base class. Its speak function behaves similarly to dogs, but produces a different sound. Unlike the dog, cats enjoy playing with anything. The describe method is inherited directly from animal base. Next, we instantiate and test the classes. A cat named Garfield, age 7, is allocated on the heap. Likewise a dog, named Lassie, age 12, with a breed of roughcollie. Finally, a generic function is invoked for both instances. It accepts a pointer to the iAnimal interface and calls the sequence describe, speak, and play, in this case with a mouse toy. The program compiles cleanly and behaves exactly as intended. Now, when we have the C++ project as a reference, let's try to do it the same in my OOP framework in Zig. In C++, we had the iAnimal interface implemented in such a way. In my OOP framework, interface declaration takes a little bit different approach. The first key difference is that interfaces are defined using a comptime function that returns a type instead of struct or class. Specifically, it returns a struct containing the interface's member functions. All functions declared within this struct are used to build a virtual table, so they are always considered virtual. Another difference is due to Zig's philosophy of transparent control flow. Virtual functions calls must be made explicitly. To support this, I added a helper function that performs the dispatch. The last difference is in the destructor member function. I had no other idea to separate virtual calls for delete, which will delegate to delete implementation, for example to release the file, and destructor call that releases memory allocated by interface instance. This will be more clear in the second part, I will try to explain it. Last thing related to interface is actual interface type creation. For that purpose, I created a comptime function construct interface that takes interface generator function and returns interface struct that contains combined interface API, VTable, and pointer to an object. Now let's move on to the animal base class. Just a quick reminder, here is how it was structured in C++. The Zig implementation is a bit different syntactically, but it achieves the same purpose. Inheritance in my OOP framework is accomplished using a comptime function called derive from base. This function returns a struct containing member functions. With Zig's using namespace feature, we can easily propagate those functions from the base to the child type, similarly to classic inheritance. Analogically to the C++ example, animal base contains member fields name and age, and describe member function. Please note that due to the type of the first argument, describe is a valid member function in Zig. Then I added exactly the same print inside describe member function. As a quick refresher, in C++ this was done by inheriting from animal base. In Zig we have exactly the same. In my current OOP framework, the base class must be explicitly declared as a base member field. This requirement is enforced at compile time, so there is no risk of accidentally omitting it. Next, I implemented the dog creation function, which serves the same role as a C++ constructor. It initializes both the dog-specific fields and the animal-base struct. After that, I added the speak member function. To access any fields defined in the base class, I simply reference the base member, making interaction with inherited data clear and straightforward. Similarly, I extended describe functionality to print an animal bred too, and I've added play. The last thing is destructor, but in my case it does nothing. The implementation for cat is almost the same, so we can skip that. The major difference is it uses animal base provided describe method instead of providing its own. So let's try using it. C++ implementation did some things with a pointer to the interface class. For my object-oriented framework, the first difference is that I can pass interface objects as copy. My OOP framework implementation uses fat pointer technique, so it contains pointer to an object and metadata, which in my case are VTable and allocator. VTable points to specific instances of VTable definition, for example for the dog. Then the pointer points to the dog object. Allocator is an optional field used when the interface is constructed with an object on the heap, and during destruction it will deallocate resources. Similarly for the cat. Just VTable pointer has different instance of VTable, and object points to cat instead of dog. So in the test animal function I called interface functions exactly the same as in C++ example. However, in Zig we don't have global allocators, so I created a general purpose allocator to create my objects on the heap. I have a way for stack-based interfaces too, but for the sake of that example, heap allocation is easier. So first I'm using create function to initialize fields, and then I'm calling new to allocate object on the heap and create interface object. Since Zig uses defer keyword as array replacement, I deferred cat destructor call. And I did the same for the dog. Then, similarly to C++ example, I called test animal for both Garfield and Lassie. Let's compile and verify if I have the same output as for the C++ example. And you can make applause now. If you're wondering how my OOP framework is implemented, let's walk through it, and you will see it's actually a pretty simple concept. I just combined three concepts. First is to use VTables for runtime dispatching. Second is to use reflections available in Zig language for Zig structs parsing. Then I combine these two things using Zig's most powerful tool, which is comptime. So starting from interface construction. It's a comptime function that takes an interface generator as an argument. Then it makes some compile time transformations, like deduction of VTable type, which finally leads to having VTable type containing member fields pointing to the specific function's implementations. Then it adds an opaque pointer to the object, an optional allocator, if heap allocation is needed, exactly as I described fat pointers. One additional thing added in interface struct type is internal destructor member function, but calls destructor via runtime dispatching. This is an area I'm still working to improve. Currently, destruction occupies two separate slots in the VTable. That's because I need to reliably dispatch destructor calls to the actual object instance, which requires knowing its original type. And the interface itself doesn't retain that type information, so the dispatch mechanism must resolve it explicitly. To complete the interface setup, the interface object is extended with member functions provided by the interface generator. This final step ensures the interface exposes the full API expected by consumers, tying together dispatching, memory management, and behavior in consistent and type-safe way. The creation of VTable type is one of the most intriguing aspects of the entire implementation. This step involves generating a Zig struct type entirely within the comptime domain. The algorithm works by traversing all declarations within the generated interface type. For each virtual method, a corresponding member field is created, represented as an optional function pointer. The optionality here is only relevant during compilation, as it helps determine whether any pure virtual functions remain unimplemented. The actual generation of the VTable type struct is handled in separate function, which I will describe later in more detail. One final but important step is injecting a virtual destructor into the VTable. This member function is internal and managed automatically, so it is hidden from the user. At the end of this process, the function returns a clean Zig struct containing only function pointer fields, serving as the runtime dispatch table. The genVTable entry function is responsible for constructing the type of a single VTable entry. This process involves evaluating several type traits to determine all necessary components that define the final entry type. The result is an optional function pointer type that accepts a pointer to the target object and takes tuple of arguments corresponding to the virtual method signature. Importantly, genVTable entry returns the actual struct field that becomes part of the final VTable layout. I needed a bridge between interface methods that takes normal arguments and VTable entries that expect a single tuple. To handle this, I wrote a getVcallArgs helper that converts a function's parameter list into the tuple form that VTable requires. Under the hood, getVcallArgs uses Zig's reflection to inspect a function's parameters at compile time. It builds an array of their types in a comptime loop, intentionally skipping the first parameter, the object pointer, which is passed separately. If you are seeing this double plus operator for the first time, it's just compile time array concatenation. Once the array of argument types is ready, I wrap it in a Zig tuple type. Now I can use regular arguments handling in the virtual calls and using tuples of arguments internally, which is much simpler to process. You may have spotted that I've used one more function called prunTypeInfo. It's a relatively simple function that changes any type of pointer to any opaque with respect to constness. Any opaque is used by function pointers inside VTable. The generate class function is the core of the framework, but constructs interface objects. It contains two main operations: building the VTable for the target type, like cat or dog, and the init function that initializes the interface object. Last but not least, it propagates the member functions from the interface. Having this, build VTable function generates a VTable object or a specific child type. It loops through every entry in the table and assigns each one to its concrete implementation. For clarity, this example shows only single inheritance. The full GitHub version walks through the right types in reverse order, treating the last child as highest priority. The critical step is binding each VTable slot to the actual virtual call. To ensure we restore the original type at dispatch, I use genVcall function, which wraps the call by casting the self pointer back to its concrete type, and finally calling target implementation. Another helper function infers an opaque pointer const qualification and then constructs the pointer type to the target object. Init function constructs a struct that holds the VTable. If you need static variable in Zig, you can create struct and keep struct type as variable, not object, but struct type. It then initializes every field on the interface type and returns the populated instance. The virtual call declaration is very easy. It looks up the function pointer in the struct and invokes it. Because we verify at compile time that no VTable entries are null, using the optional access operator is completely safe. We also need a destructor call, but this is simple too, it just forwards the call to the object. I've described the interface object creation part. Now let me briefly explain the inheritance part. It is as simple as defining another struct that implements the interface's object creation methods. In a dedicated member function, you allocate memory, construct the object in place, and return the initialized interface object. The destructor simply frees that memory, and it's called by the framework only when the allocator field is set. That's it for today. I hope I made OOP concept clear and approachable. If you'd like to try it, head over to the GitHub repository. There is readme how to set up environment and how to inherit the module into your project. I hope you find that video useful, whether you pick up something new or you just enjoy it. Thank you for watching until very end. If you like it, please share it with others. Wishing you a fantastic day or night, whenever you are. Thank you for today, bye and see you soon!